Welcome to my channel. In this lesson, we will learn about experimental observations made by scientists and proposed different atomic models. Let's begin. The existence of atoms has been proposed since the time of early Indian and Greek philosophers, who were of the view of that atoms are the fundamental building blocks of matter. According to them, the continued subdivisions of matter would ultimately yield atoms, which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncuttable or non-divisible. These earlier ideas were mere speculation and there was no way to test them experimentally. These ideas remained dormant for a very long time and were revived again by scientists in the 19th century. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton. He was a British school teacher. In 1808, he presented his atomic theory, which was a turning point in the study of matter. In his theory, he stated that elements consist of atoms. So, all matter is made of very tiny particles called atoms which participate in chemical reactions. See the example, an atom of oxygen element and an atom of hydrogen element. Second, identical atoms in an element. So, all atoms of a given element are identical in mass and properties, but they differ from those of other elements. See example, oxygen element have same mass and properties of atoms, but they are different from other hydrogen elements of atoms. Next, atoms cannot be created or destroyed. So, atoms are indivisible particles which cannot be created or destroyed in a chemical reaction, but these atoms can be rearranged, combined, or separated in a chemical reaction to give new product. And last one, compounds formed by combining atoms. So, compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kind of atoms. See the example, two hydrogen elements when they are reacted with oxygen atoms, two oxygen atoms, it gives two molecules, two water molecules. So these are the postulates of Dalton's atomic theory. Limitations of Dalton's atomic theory. In his theory, it does not account for the subatomic particles, that is electrons, protons and neutrons. And second point is it doesn't account for isotopes. Isotopes means the same atomic number and different mass numbers. See the isotopes of hydrogen having same atomic number but shows different mass numbers. According to his theory, identical atoms have same mass number, but here these isotopes shows different mass numbers. And the third point is it does not account for isobars. Isobars means same mass number but different atomic numbers. See the example, argon, potassium and calcium having different atomic numbers but they have same mass numbers. So why these elements having same mass number, he didn't explain. And fourth one is elements need not combine in simple whole number ratios to form compounds. See the example, certain complex organic compounds need not combine in simple whole number ratio. Last one, this theory does not account for allotropes. So allotropes means they have same property, some chemical elements to exist in two or more different forms. So this is called allotropes. Example, carbon, diamond and graphite. So why these allotropes are formed, what is the property of this, he did not explain. So these are the limitations of Dalton's atomic theory. Later, J.J. Thomson, an English scientist, proposed the famous Thomson atomic model in the year 1898, just after the discovery of electrons. So, this was the first scientific model to describe the internal structure of an atom. Thomson proposed that the shape of an atom resembles that of a sphere having a radius of 10 to the power of minus 10 meters. So the positively charged particles are uniformly distributed with electrons arranged in such a manner that the atom is electrostatically stable. Many different names are given to this model, for example, raisin pudding, plum pudding model, or watermelon model. So, here the embedded electrons resembled the seeds of a watermelon, while the watermelon's red mass represented the positive charge distribution. This plum pudding atomic theory assumed that the mass of an atom is uniformly distributed all over the atom. So the drawbacks of this atomic theory, it failed to explain how the positive charge holds the electrons inside the atom, and it also failed to explain the reasons for the stability of an atom. The plum pudding atomic model lacked experimental evidence, and hence Rutherford conducted many experiments in order to determine the structure of an atom. Rutherford and his students Hans Geiger and Ernest Marsden bombarded very thin gold foil with alpha particles from a radioactive source that was directed at a thin foil of gold metal. The thin gold foil had a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck the screen, a tiny flash of light was produced at that point. So, the result of this scattering experiment was quite unexpected. According to Thomson model of atom, the mass of each gold atom in the foil should have been spread evenly over the entire atom, and alpha particles had enough energy to pass directly through such a uniform distribution of mass. He expected that the alpha particles would slow down and change directions only by a small angle as they passed through the foil. But he observed that most of the alpha particles passed through the gold foil without deflecting. Some alpha particles were deflected by small angles and some were deflected by nearly 180 degrees. So, on the basis of these observations, Rutherford drew the following conclusions regarding the structure of atom. Most of the space in the atom is empty, as most of the alpha particles passed through the foil undeflected. A few positively charged alpha particles were deflected. The positive charge has to be concentrated in a very small volume that repelled and deflected the positive charged alpha particles. So the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 to the power of minus 10 meters, while that of nucleus is 20 to the power of minus 15 meters. Example, if a cricket ball represents a nucleus, then the radius of atom would be about 15 kilometers. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom. So according to this model, the positive charge and most of the mass of the atom densely concentrated in extremely small region. So this very small portion of the atom was called nucleus by Rutherford. The nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system in which the nucleus plays the role of sun and the electrons play the role of revolving planets. Third, electrons and the nucleus are held together by electrostatic force of attractions. So this model drawbacks. According to electromagnetic theory of Maxwell, charged particles when accelerated should emit radiation. An electron in an orbit emit radiation, so the energy carried by radiation comes from electronic motion. Orbit will thus continue to shrink, but this not happen. Rutherford model cannot explain the stability of an atom, how electrons are distributed around the nucleus. So these are the drawbacks of Rutherford model. So light is the form of radiation known from early days and speculation about its nature. James Maxwell was the first to reveal that light waves are associated with accelerating electric and magnetic characters. He suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the form of waves called electromagnetic waves or electromagnetic radiations. So these waves do not require medium. It can move in vacuum. There are many types of electromagnetic spectra radiations which differ from one another in wavelength. These constitute called electromagnetic spectrum. Different regions of the spectrum are identified by different names. See the examples. So here an electromagnetic spectrum can be described in terms of four quantities, that is wavelength, wave number, frequency and velocity. See the first one, wavelength. Here the highest surface part of a wave called crest and lowest surface part of a wave called trough. The distance between two consecutive crest or trough called wavelength. So it is represented by lambda units, meters, micrometers or nanometers. Next one is wave number. It is defined as the number of wavelengths per unit length is called wave number. It is represented by nu bar, units per centimeter or per meter. Next, frequency. It is the number of waves that passes a given point in 1 second is called frequency. So it is denoted by nu, units per second. Last one is velocity, the speed of light in vacuum, commonly denoted c. So these are the important terms we should remember. Demerits of wave theory. Maxwell's suggestion about the wave nature of electromagnetic radiation was helpful in explaining phenomena such as interference and diffraction, but it couldn't explain about the nature of emission of radiations from hot bodies, photoelectric effect, variations of heat capacity of solids as a function of temperature, and line spectra of atoms with spectral reference to hydrogen. Here we should know black body radiations and photoelectric effects. So what is black body radiation? The phenomena of black body radiation was given by Max Planck in 1900. When solids are heated, they emit radiation over a wide range of wavelengths, means when ideal body which emits and absorbs radiation of all frequencies is called a black body, and the radiation emitted by such a body is called black body radiation. Here, the exact frequency distribution of the emitted radiation from a black body depends only on its temperature. So this is the black body radiation. Next, photoelectric effect. In 1887, Hertz performed a very interesting experiment. The electrons are ejected from the clean metal like potassium, rubidium and cesium surface. As soon as the beam of light strikes the surface, that is, there is no time lag between the striking of light beam and the ejection of electron from the metal surface. The number of electrons ejected is proportional to the intensity or brightness of light. For each metal, there is a characteristic minimum frequency are also known as threshold frequency. The kinetic energy of these electrons increases with the increase of frequency of the light used. The kinetic energy of ejected electron is given by the equation h nu is equal to h nu naught plus half me v square. Here me is the mass of the electron, nu is the v is the velocity associated with the ejected electron. More intense beam of light consists of larger number of photons. So Albert Einstein received the Nobel Prize in Physics in 1921 for his explanation of photoelectric effect. On the basis of wave theory of light, The German physicist Max Planck in 1900 proposed a quantum theory. According to this theory, atoms and molecules could emit and absorb energy only in discrete quantities and not in a continuous manner. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy of a quanta of radiation is proportional to its frequency and is expressed by equation E is equal to h nu. Here, the proportionality constant h is also known as Planck's constant and has the value 6.626 into 10 to the power of minus 34 joule second. With this theory, Planck was able to explain the distribution of intensity of the radiation from black body as a function of frequency or wavelength at a different temperature. Later, in the year 1905, Albert Einstein also reinterpreted Planck's theory to further explain the photoelectric effect. So finally, scientists accepted that the idea of light possesses both particle and wave-like properties. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. So it is observed that when a ray of white light is passed through a prism, the wave with a shorter wavelength bends more than the one with a longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out into a series of colored bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shorter wavelength, is deviated the most. The spectrum of white light that we can see ranges from white light to red light. Such a spectrum is called continuous spectrum because violet merges into blue, blue merges into green, and so on. A similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation. So here the spectrum of radiation emitted by a substance that has absorbed energy is called as emission spectrum. Atoms, molecules or ions that have absorbed radiation are said to be excited state. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength of the radiation emitted as the sample gives up the absorbed energy is recorded. An absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelengths. The missing wavelength, which corresponds to the radiation absorbed by the matter, leave dark spaces in the bright continuous spectrum. So the study of emission or absorption spectra is referred to as spectroscopy. Here, the emission spectra of atom in the gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather than they emit light only at specific wavelengths with dark spaces between them. Such spectra are called line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the hydrogen molecules dissociate and the energetically excited hydrogen atoms are produced. These hydrogen atoms emit electromagnetic radiations of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverer. Balmer showed in 1885 on the basis of experimental observations that if spectral lines are expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey the following formula, that is wave number equals 109,677 into 1 upon 2 square minus 1 upon n square centimeter inverse. So where n is an integer equal or greater than 3. The series of lines are described by this formula are called Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. Then the Swedish spectroscopist Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expression, that is wave number 109,677 1 upon n1 square minus 1 upon n2 square centimeter inverse. Here n1 1 comma 2 comma and so on, n2 is equal to 1 plus n1 plus n1 plus 2. The value of 109,677 centimeter inverse is called the Rydberg constant for hydrogen atom. So the first 5 series of lines that corresponds to n1 is equal to 1 comma 2 comma 3 comma 4 5 are known as Lyman, Balmer, Bastian, bracket and P-Fund series. See the series of first one is Lyman series. It is the series of emitted light if the transition occurs between the first and any other energy level are called Lyman series. It is observed in ultraviolet region of electromagnetic spectrum. Second, Balmer series. It is the series of transition between the second and any other energy level. So here this Balmer series we observed in visible region of electromagnetic spectrum. Next, Paschen series. It is the transition between the third and any other energy level. It is observed in infrared region. Next, bracket series. It is the transition between the fourth and any other energy state. It is also observed in infrared region of electromagnetic spectrum. Last, P-Fund series. It is the transition between the fifth and any other energy state. It is observed also in infrared region of electromagnetic spectrum. So these are the line spectrum of hydrogen. Niels Bohr was the first to explain quantitatively the general features of hydrogen atom structure and its spectrum. Though the theory is not the modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectra. Bohr's model for hydrogen atom is based on the following postulates, that is, electrons revolve around the nucleus in a circular paths called orbits. Orbits are denoted by 1, 2, 3 or K, L, M, N and so on. Each orbit is associated with a definite amount of energy. Hence, these orbits are called energy orbits. The circular orbits are represented by the letter n, which represents principal quantum number. As the value of n increases, the size and energy of the orbit increases. As long as the electron revolve in the circular orbit, they neither emit nor absorb energy. Hence, these orbits are called stationary orbits. When electron jumps from higher orbit to lower orbit, it emits energy. When electron jumps from lower orbit to higher orbit, it absorbs energy. So the energy emitted or absorbed is given by delta E is equal to E2 minus E1. Here delta E is equal to difference in energy, E2 is equal to energy of higher orbit and E1 is energy of lower orbit. So the angular moment of an electron is integral multiple of h by 2 pi. Limitations of Bohr's model of atom. This model failed to explain the atomic spectra for elements containing more than one electron. When the hydrogen spectrum is observed by using a spectrometer of high resolving power, it is observed that individual lines are not single but consist of several fine lines lying close together. Such a hyperfine spectrum could not be explained by this theory. The model fails to explain the splitting of atomic spectral lines in the presence of an external magnetic field and external electric field. It also failed to explain the ability of atoms to form molecules by chemical bonds. So these are the limitations of Bohr's model of atoms.